In the previous lecture, we learnt about capacitor and inductor. We know very well about capacitor and inductor. In this class, we are going to discuss about C oscillation. L for inductance, C for capacitance. Okay. What is the energy stored in the capacitor? In the capacitor, the energy is stored in the form of electric field, that is electrostatic potential energy. In the inductor, the energy is stored in the form of magnetic field, that is magnetic potential energy. So, the two energies are different. When the capacitor and inductor both are connected in a circuit and the energy is applied in the circuit. Okay, when both are connected in the circuit, the energy was produced. What is the type of energy? There is a combination of electric field and magnetic field. The energy oscillations are produced. These energy oscillations, why I am said oscillation means the energy oscillates back and forth between the capacitor and the inductor. Due to the movement of the energy, the transfer of energy back and forth, there is an oscillations are produced. These type of oscillations are produced due to the effect of inductor and capacitor. So this type of oscillations are called as C oscillations. C oscillations. This is a very important question. One of the important question. So you please listen. C oscillations. How the C oscillations are produced? How the C oscillations are sustained? Is it damped or undamped? There is a lot of questions. Now we are going to discuss about that. Let us consider a circuit containing. This is the first step. Look at the diagram. A circuit containing a capacitor and the inductor. Here the capacitor is fully charged, so the current passes through the circuit is said to be 0. Assume that. Okay, the capacitor is fully charged. Here the capacitor is fully charged, so the total energy is only electric field, due to the electric field. Here the notation of the energies is given. UE represent electrical energy, UB represent magnetic energy. Here only electric energy is there. That means the capacitor is fully charged. Here the energy is fully electrical. There is no magnetic energy. In the first case, there is no flow of current here. Okay, in the first step. Okay, in the step 2, the capacitor begins to discharge. Here the capacitor begins to discharge. So the charges are moving. As a result, there was a current passing through the inductor. So due to the passage of the current inside the inductor, there was a magnetic field produced around the inductor. That means magnetic potential energy is stored in the inductor. So here the current flows through the clockwise direction. Here capacitor have some charge, but not fully charged. The capacitor is discharged. So part of the capacitor is charged. 50%, for example, 50% of the capacitor is charged. Remaining charges goes through the inductor. It produces magnetic potential energy. So in this case, the total energy is equal to sum of the electrical energy and the sum of the magnetic energy. In the first case, the magnetic energy is 0. So only electrostatic potential energy, that means electrical energy is there. So we can write the expression UB is equal to 0, and UE is equal to Q square by 2C. Here I am using capital letter QM. QM means the charge is maximum. Here the capacitor is fully charged. So we are writing QM square by 2C. This is the expression for first case. UB is equal to 0, UE is equal to QM square by 2C. In the second case, in the second step, there are two energies. One is electrical energy, another one is magnetic energy. So the total energy is equal to sum of UE plus UB. Where UE is what? UE is electrical energy, so it is Q square by 2C. Here we are writing small q because the capacitor is allowed to discharge. So only we are using small q. UB is the magnetic potential energy, that is half L I square, because the current flowing through the circuit is I. So this is the expression for second step. Here two energies are present. The total energy sum of the two. Don't forget this. This is one of the important thing. The next step number 3. Here the full charge. Here the full charge of the capacitor was discharged, and all the charges are moving and goes through the inductor. So the current passing through the inductor is maximum here. So here the magnetic field produced is also maximum. So in this case the current passing through it is maximum, which is along the clockwise direction. In this case the energy of the capacitor, the energy due to the capacitor U is 0, the energy due to the inductor UB is maximum, because the maximum current flows through the circuit. So in this case U is equal to 0, UB is equal to what? Half L Im square. This Im represents maximum current. That means maximum possible current passing through the inductor. So it produces the maximum magnetic field, the maximum magnetic potential energy. So in this case the total energy is wholly magnetic. There is no electric component, there is no electric potential energy here. This is for step C, step 3. The next, the fourth step. Look at the fourth step. Here the full charge of the capacitor was discharged, and this all the charges are goes to the inductor itself. But here one important thing I want to tell you, but the inductor does not stop the current immediately. All the charges are going to the inductor. So there is no, if we imagine here there is no current flows through the inductor, but that is not correct. Because due to the property of the self-induction, the inductor does not stop immediately the current pass through it. Does not stop immediately. It will not stop immediately. Okay, so there is some current flows through the inductor in the clockwise direction itself. That means here the current is 0, here the current is increasing, here the current goes to maximum, here the current is decreasing. I just draw a diagram here. First step, the current is 0, okay. The second step, the current is increasing. The third step, the current goes on increasing and it attains the maximum. In the fourth step, the current does not immediately comes to 0 because of the self-induction. So the current decreases. This is the step number 4. Here the current decreases, but they are moving in the same direction. So in this case, the capacitor, in this case the current decreasing but moving in the same direction, that is clockwise direction. So here the maximum magnetic field around the inductor is collapsed. The maximum magnetic field around the inductor is collapsed. Due to this confusion, the capacitor begins to discharge in the opposite direction, because we know the property of the self-induction. When the current is increasing, the induced EMF opposes the growth of the current. When the current is decreasing, the induced EMF try to increase the growth of the current. We know very well. It try to prolonging the increase or decrease the growth of the current. So here the current is decreasing, so the induced EMF due to the self-induction tries to decrease the growth of the current, decrease the decay of the current, because here the current is decreasing. So the induced EMF tries to decrease the decay of the current. So the capacitor is charged in the opposite direction. Look at the direction here. Here plus minus, here plus minus. Okay, so the plus minus, yes. So the capacitor begins to charge in the opposite direction. So in this case there was a electrical energy as well as magnetic energy. The energy is split. So there is electrical energy as well as magnetic energy. So in this case the total energy is equal to sum of the electrical energy as well as magnetic potential energy. Both energies are present in this case. In this case, two important things I tell you. One is the direction of current and another one is the charging of the capacitor in the opposite direction when compared to the first case. Okay. The next step. In the next step, the current goes on increasing and it goes to zero position. So there is no current flows through this. In this condition, the magnetic energy is fully converted into electrical energy. So there is no current flows through the capacitor because the capacitor is fully charged in the opposite direction. Note this, in the opposite direction the capacitor is fully charged. Here there is no part of the inductor, so there is no magnetic field here, so there is no magnetic potential energy. Only electrostatic potential energy is here. In this case the total energy is electrostatic potential energy or electrical energy. There is no magnetic energy here. Okay. The next step. Here look at this step. This step is similar to the first step. Here first step the capacitor is fully charged. Here also the capacitor is fully charged, but the only difference is the capacitor is oppositely charged. Here the capacitor is oppositely charged. Remaining all things are same here. Here also current is 0, here also current is 0. These two steps. Here also current is 0, here also current is 0. But here what is the only one difference? The capacitor is charged in the opposite direction. Okay, we will move to the next step. In the next step, the capacitor is allowed to discharge. So due to the discharge of the capacitor, there is an establishment of current, but the direction of current is in the anti-clockwise direction. Look at the direction of current here. This is opposite to this case. Here the direction of current is clockwise. Here the direction of current is anti-clockwise because the capacitor is discharged. So part of the charges are going to the inductor. So there was a production of current. So the current is in the anti-clockwise direction. Here the two energies are present, electrical energy as well as the magnetic energy. The next case, this is opposite to this case. What here? Here also maximum current flows, here also maximum current flows. The only difference is the direction of current. Otherwise the same thing are repeated here. Here the energy is wholly magnetic. This case is opposite to this. Yes. This case is opposite to this. That means the current is going in clockwise direction. Here the current is going in the anti-clockwise direction. Here also the current will not immediately comes to 0 because of the inductance. So the current, the value of the current decreases here. So the value of the current decreases here. That means this position. This is what this and this position here, and this position is negative, maximum is here. And then the current changes its direction. When the current changes its direction, at that point the capacitor is charging in the opposite direction. So first step, the capacitor charging in one direction. Here the capacitor is charging in the opposite direction. Here the capacitor is charging in the opposite direction to this case, and this is similar to this case. Look at the diagram. This is the step here. Okay, the next step, the last step, the current becomes 0. The current becomes 0. Here the current becomes 0 because the capacitor is fully charged here. So this is the one cycle of LC oscillation. So in this way, the current wave was produced. This looks like a sine wave. Look at the diagram. This is a exactly sine wave. This type of sine waves are produced due to the energy conversion between capacitor and inductor. Here the energy is transferred from capacitor to inductor, inductor to capacitor. Here the energy is moving back and forth, oscillating back and forth between the capacitor and inductor. So it produces oscillations of definite frequency. It produces oscillations of definite frequency. These type of oscillations are called as LC oscillations. These LC oscillations are most important thing. This will be used in, it has several applications. Okay, in future we will going to discuss about this. Okay, in this LC oscillation there is a energy transformation between inductor and a capacitor. So oscillations are produced with a definite frequency. That is the most important word. Okay, when the energy is transferred from inductor to capacitor or capacitor to inductor, is there is any loss of energy? That is the one question. Is there is any loss of energy? Say yes. Say yes. Yes. Yes in the practical cases. But for an ideal inductor and ideal capacitor, that means in an ideal case, there is no loss of energy. It obeys law of conservation of energy in the ideal case. So the energy can't be destroyed, the energy can never be produced. So one form of energy is converted into another. Magnetic energy is converted into electric, electric energy is converted into magnetic, only in the case of ideal. Okay, so in the case of ideal, ideal inductor, ideal capacitor, LC oscillations of definite frequency are produced. It should be a undamped oscillations. Undamped means there is no change in the amplitude till the end. Till the end there is no change in the amplitude. These type of oscillations are produced. This type of undamped oscillations are produced in the LC oscillations of ideal case. But in practice there is a loss of energy due to Joule's heating effect. So the oscillations are not undamped, the oscillations are damped oscillations are produced. The damped oscillations are produced. What is the diagram for damped oscillation? The diagram for damped oscillations is the amplitude goes on decreasing with respect to time. So the amplitude goes on decreasing and it vanishes at a particular time. These type of oscillations are called as damped oscillations. Why the LC oscillations are damped? Because of the Joule's heating effect. There is a loss of some energy. Due to the continuous loss of some energy, the total oscillations the total oscillation are vanished in a particular time. This type of oscillations are called damped oscillations. Okay, how we can produce undamped oscillations in practice? Is there is any possibility to produce undamped oscillations? Yes. The output we are giving some external agency, some external force or external agency to maintain these oscillations, to maintain the amplitude of the oscillation. Then we can produce undamped oscillation. For this we can make use of the feedback. The output, a small portion of the output is taken and it is fed into the input. That is the external agency here that produces undamped oscillations. Okay. In this class we are studied about the LC oscillations in detail. Here the cycle of the LC oscillation. First case, here A, there is no current. Here current is increasing. Here current goes on maximum. Here the current starts on decreasing, so the capacitor begins to discharge in the opposite direction. Here then the current goes to 0. Okay, here the current negative direction 0. Then the direction of current changes. The direction of current is anti-clockwise here. So the direction of current is anti-clockwise here. Then the direction of current is anti-clockwise, but the current goes on maximum. Then the current goes in the anti-clockwise direction, but the current decreases, then the current goes to 0. So this, due to the change of the current, due to the changing value of the current, LC oscillations are produced. These the shape of the LC oscillations are in the shape of sine waves. Okay, we will discuss detail about the LC oscillations in this class. We are going to discuss a new topic in the next chapter. Okay, till that, thank you my dear friends. Thank you. Bye.